Work done by a constant force. Work is done on an object when a force acts on the object, causing the object to move in the direction of the force. If I want to move this box across the floor, I apply a force on it to the right, and if the force is great enough, the box moves across the floor in the direction of the applied force. Since the box moved in the direction of the applied force, work was done on the box. Let's say the displacement of the box that I move is given by S. Let's also say that the positive direction is to the right. In this case, the net force on the box is in the same direction as the displacement of the box, and the work is found by multiplying the magnitude of the force and the magnitude of the displacement. What if I'm pushing the box to the left instead of to the right? Since left is in the negative direction, the magnitude of our force is negative F, and the magnitude of the displacement is negative S. When we multiply these two negative values together, we of course get a positive value. So the amount of work is the same even if I'm pushing the box to the left instead of to the right. Since the amount of work does not depend on direction, work is a scalar quantity. Work depends on both force and displacement. So if I were to apply my same pushing force to a much more massive box that did not move, is any work being done on the box? Since the box doesn't move, displacement is equal to 0, and work is therefore equal to 0. So, if an object does not move, then no work is being done on it, no matter how much force is applied to it. Work can also have a negative value. If the applied force is in the positive direction and the displacement is in the negative direction, then the force has a positive value and the displacement has a negative value. Multiplying these together to find the work, you will get a negative value for your work. The units of work are given as force units multiplied by displacement units, that is newtons times meters. A newton meter is also called a joule. Sometimes the net force on an object and the object's displacement might point in different directions. Let's say, for example, that I attach a rope to a box and I pull diagonally on the box, moving it across the floor. The displacement of the box was to the right, even though the net force on the box was in a direction theta degrees above the right. The box moved to the right because the force has a component in that direction. The force has a vertical component and a horizontal component, and the horizontal component directed to the right is what caused the box to move to the right. In our previous example, the net force on the box was in the same direction as the displacement of the box. We saw that, in this case, the work was found by multiplying the magnitudes of the force and the displacement. This is only valid when the net force and the displacement are in the same direction, so it would not work in our current case. The more general way to calculate the work is to multiply the force and displacement vectors in a dot product. Remember that to take the dot product of two vectors A and B, you multiply the magnitudes of the vectors together and then multiply by the cosine of the angle between them. So our expression for work becomes F times S times the cosine of theta. Using trig to calculate values for the horizontal and vertical components of the force, we find that the magnitude of the horizontal force is equal to F times the cosine of theta. So, for our work, we're multiplying the magnitude of the displacement by the magnitude of the component of the force that's in the same direction as the displacement, just as we did previously. It's just that in our previous case, the force vector and the displacement vector were in the same direction, which means that the angle theta was equal to 0. The cosine of 0 degrees equals 1, so in this case, F times S times cosine of theta simplifies to F times S. It's also important to note that the component of the force perpendicular to the displacement of the box did no work on the box. In this case, that was the vertical component, F times sine of theta. Only the force component that was parallel to the displacement did. Let's do an example problem. How much work is done on the box by my 22 Newton pulling force if I am pulling at an angle of 25 degrees above the floor for a distance of 7 meters? First, what are we given? The magnitude of the pulling force is 22 newtons. The force is directed 25 degrees above the floor. And the box is displaced by 7 meters. And we're looking for the work done on the box. So what equation can we use? Work equals the magnitude of the force multiplied by the magnitude of the displacement multiplied by the cosine of the angle between the two vectors. Now we just plug in our known values for F, S, and theta, and using our calculator, we get a value of 140 joules for the work done on the box.